Okay, welcome back. This is lecture 10 of wireless without batteries. And last lecture, we studied inductive information transfer. We talked about overcoupled system, wireless power transfer through induction, and we had a little talk about near-field communications. And you basically have readings for those topics up on the website under the resources page. Lecture 9, I think it's labeled as reading 9, is a paper by Alance and Sample and Company. A great paper just demonstrating the analysis and measurement and a really nice breakdown of how an inductive overcoupled wireless power transfer system works. Lecture 10, which was really at the end of lecture 9, that was NFC. There's the Fischer paper on that. That doesn't have a lot of meat to it. That was sort of a survey paper that was in IEEE Communications magazine. You don't have to do a really deep analysis for NFC. I think it's just a neat application for some of the things that we've been talking about over the last week. And as a result, this class period, rather than delving deep into NFC communications, I threw it all in the last lecture, and I'm going to use this class period as recitation preparation for your test. So basically, we'll just hang around, talk about questions. You can ask questions about the material. I have a few sample problems I brought that maybe we can work together. And then when we're done, we're done. You can go off and study for your midterms, your ample number of midterms that you're preparing for. You have, for the in-class students today, homework 3 is due today. Homework 4, which shouldn't be that involved, that's inductive and magnetic field modeling, that's Friday. And then we said homework number 5 would be due on March the 1st. And of course, if you're a DL student, +7, +7, +7. Let's see. Is there anything else, any other questions you have administratively? Of course, we have a test on Monday. And that means there will be a window from the 20th to the 27th for arranging that with your distance learning proctor. And then when we're back, when our test is done next Wednesday, we'll start talking about less about energy harvesting and transfer and more about information transfer. That's where we get more into telecommunications and do a little coding theory, a little backscatter modulation, talk about some interesting technologies for exchanging energy and information with minimal amounts of power. And I also hope the following week after next to give you some tentative project titles that you can select from, or if you have your own ideas on what you want to study, then you'll have a couple weeks to prepare a little proposal telling me what you want to study. And then your term papers will be due sometime in like mid to late April, before the semester is over, but after the lectures stop at the end of March here in Shenzhen. So it should be nice. You have plenty of time to work on your project, unmolested by a professor that's always making you attend lectures. There is no final exam in this class, so that test 2 that we have the last week of March will be the last test you'll take. That'll just count just like test 1. So, okay. No more questions? So let's go ahead and I've got some old test questions here in front of me. Many of them would be fair game on the test, but not all of them. I've taught this class once before, and at maybe only 50 or 60% of the topical material is the same. Tweak things, it's kind of an early class, and so it hasn't solidified yet. And plus, even when I've taught something a lot of times, I just get bored with teaching the same thing, so I always add new lectures and take new lectures out. I'm constantly tinkering with courses on what to do. So anyway, I have to go through here and see which of these test questions would actually apply to you. So one here I have right in front of me, it's called path loss modeling. This one would be fair game. And there's a picture on this one. Let me see if I can draw the schematic quickly. This is some sort of schematic here of a building layout. Like an office building of some sort, maybe. And what we have here is a soft partition. That would be like a cubicle, a temporary wall or a modular furniture wall. A hard partition, this would be like plaster, or probably what's behind me right here. And then we've got an exterior wall. This would be brick and steel or something kind of generally more lossy. And then in this diagram, there appears to be a transmitter, a wireless transmitter in the closet here. We're trying to figure out how much power gets to these spots. And these are labeled. It says, below are 4 path loss measurements with respect to 1 meter free space made in a small office building. And they're labeled on the diagram. This is 76 dB, not dBm because it's path loss. It's not milliwatts or watts. So it's path loss with respect to 1 meter free space. 72 dB, 35 dB, 56 and 76. And it says, you are going to use these spot measurements to construct a partition-based model for planning a wireless LAN. Construct a system of equations in matrix form that allow you to calculate partition values for hard cinder block walls partitions and soft drywall partitions. You may make rough estimates of distances. So there's actually a little scale down here. 10, 20, 30, 40, 50 meters. You may make a rough estimate of distances. Do not solve for these optimum parameters. Just set the problem up. Because this is a test, for crying out loud. I don't need to test your ability to program MATLAB or something. I know you can do that by now. I just need to know that you conceptually understand the problem. And so you've got your path loss values here. Remember how we do this? There was this B matrix, and we would put our path loss with respect to 1 meter free space. And actually, we populated it with whatever the path loss was. In this case, we've got 35 dB, and another measurement at 72 dB, and another measurement at 56 dB, and another measurement at 76 dB. And from each of these, we subtracted off 20 log base 10, the free space path loss distance, right? Because in the Seidel-Rappaport model, that's what this is called, the path loss is considered to be free space path loss plus partition-based factors, whatever's in between you and the transmitter. And that's not to say that this wall, if I took it into an anechoic chamber and put a transmitter on one side and a receiver on the other side, that I would get 4 dB or whatever the Seidel-Rappaport coefficient would be for that. That's not what it's saying. It's a trend spotting tool. It says on average, that's the kind of loss that you would expect when 1 or 2 or 3 of these things is in between you. In truth, it's a very complicated electromagnetic problem. Every wall is going to be a little bit different depending on what's on the inside. Where it looks homogeneous from the outside, but there are studs, sometimes metal, sometimes wood, and where you excite it relative to your position of those studs can change. The angle that you make will change the transmission coefficient. So to take this model with a grain of salt. However, we still have to subtract off the free space. And keep in mind, this is setting up the model. I don't care that you have like some innate, if you remember to bring your Wiener calipers and can measure within a fraction of a millimeter the distance here, I don't care. I don't care. This is about the level of precision that I'm expecting when I say sketch or set up or analyze. Like look here, like I look at that. Oh yeah, that's 10 meters. Look, I measured that so precisely. And that is 35 meters. 20 log 10, 35. And let's see. Oh, this is a little bit more. I'm going to call that 40 meters. Log base 10, 40. And yeah, look, this is even a little bit further away, so I'm going to call that 41 meters. I don't know, 42 meters. Done. Done. I've got a B matrix. And the Seidel-Rappaport model, well, in this case, I've only got 2 because all the locations are indoors. I don't have to go through an exterior wall. So I really only have 2 parameters that I'm solving for. My X, call it a soft partition, and an X hard partition. And then I just need an A matrix, which should be 4 rows by 2 columns. This is A. This is my X vector. And I'm just counting at this point. And again, some of these are going to be judgment calls, right? Depending on how, obviously I've drawn a diagram with computer-like precision, but it's probably going to be a little bit different than the diagram that I have here. It doesn't matter. It doesn't matter. We just need to know soft partitions. How many do we go through? Looks like we go through that one right there. Well, let's do this one first. This one goes through 1 to the 35 dB, so I'm just going to put a 1 there. How many hard partitions does it go through? It looks like 1. Yeah, you got it. So then through here, looks like it might go through 2, so I'm just going to put 2 hard partitions down there for the second point, and 0 soft partitions for that 72 dB point. And I got the 56 dB one. Man, that one goes straight down the hallway. I'm just going to put 0 here. Oh, wait. No, wait. I go through this one, don't I? Yeah, I do 1. Do I call that a hard or a soft? Hard. Otherwise, straight down the hallway. And then this guy over here, I go 1, 2, 3, 4. Oh my, he's going to be really lossy. It looks like it goes to a soft partition too. I'm going to put 1 soft and 4 hard. And not surprisingly, he's the lossiest point there, so that's kind of consistent data with the physics that's going around. And then, how do I solve for X? X is equal to A transpose A, invert AT. But of course, you didn't even have to solve this. You could just leave it at this point. You're done. You're done, McQuaid. You don't have to invert matrices on an hour-and-a-half test. It's not fair. I'm not going to torture you with that. There, I can clearly see you've set the problem up right. Full credit. A. If this was the only problem on the test. So we only have like 1 or 2 lectures on propagation. It's an important part of this class to figure out how much power you can get from point A to point B, because that's the showstopper. That's always the showstopper, even if you're designing a wireless LAN link or a satellite link, a cellular link. Power is always the showstopper in communications. However, it's particularly important for us since we're intentionally working on the fringe of low power, both for communications and also potentially harvesting that power to use for something useful. Okay, and then any questions on that problem? Great. Let's try another one. Okay, here's another example problem, but example 2. It says you are attaching an RFIC, that stands for Radio Frequency Integrated Circuit, to an antenna with RA plus JXL, where XL is a positive number, so this is an inductive reactance. Answer the following questions based on this scenario. So let's start with this one. If the capacitive, question A is, if the capacitive portion of the RFIC's impedance, that is RIC minus JXIC. In this case, XIC is positive and it represents the negative reactance of a capacitor. You have RFIC as an energy harvesting chip, it probably presents a capacitive load to an antenna, because what is diodes look like capacitors in RF, and capacitors look like capacitors in RF, and that's pretty much all you've got, right? Diodes and capacitors presenting, no matter how you filter charge. The only exception there is that often the leads, when you have a chip and you're making an integrated circuit, the leads attaching to those chips are very thin wires, and that can often introduce inductance. In a few cases, enough inductance to actually resonate out that capacitance. In some instances, too much inductance, and you actually choke off the RF signal, because inductors look like close to open circuits if you get the frequency too high. So it really depends on how they've attached or packaged the chip. You know, you get a chip from the manufacturer, it's just a little sliver of silicon. But you don't buy the little sliver of silicon from, you know, an electronics vendor. You get it packaged, and there are lots of different ways to package the same thing, right? You could get some encapsulant, and sometimes the one that always drives me crazy is when they wire bond the things. RF, that's almost impossible to work with, because if you go high enough in frequency, these tiny little wires that they use to bond the pins of the package to the actual chip interconnects are like really high inductors. They're so thin. The thinner a wire gets, the more its per unit length inductance increases, because the current gets concentrated down into such a small pipe. And in that case, that tends to wreak havoc on RF. Anyway, back to our problem at hand. If the capacitive portion of the RFIC's impedance is this, and it is already conjugate matched, or conjugate matched, so that X of L is equal to X of C, what should RIC be to maximize power? This is easy. And it's a giveaway because it's only worth 5 points. What should RIC be? RA, of course. Freshman circuits. Oh, but it gets harder. Repeat A, but choose RIC to maximize voltage. RFIC. What should that be? What load should you pick to maximize the voltage across the integrated circuit? This one's not too bad either. Not a trick question. As hard as it looks. Let's see if I can find it. Most of you should be able to do this intuitively, but just in case, let's look back on the cheat sheet. The amplitude at the terminals of the antenna, or the terminals of the chip in this case, is equal to magnitude ZL square root of 2 PR RA over ZL plus ZL. And in this case, we said that we already know that this is going to be the conjugates are matched, so this is really RA plus RIC. This is going to be RIC minus JXIC, and that's all we know about this system. So what should I pick RIC to maximize VA? Well, generally speaking, you want it to be as large as possible, right? An open circuit would maximize the voltage in the system, right? It shows up in the numerator and the denominator. And there could be a condition here, right? You could say, well, VA is equal to 2 square root of 2 PR RA RIC squared plus XIC squared. And then divided by, what was it, just divided by RA plus RIC. So you have, for very large values, when RIC approaches infinity, an open circuit, then RIC squared dominates in the numerator. This term goes away, and you get a net to RIC there. And of course there's also an RIC that dominates in the denominator. So you wind up basically getting this 2 times 2 p sub r RA as your voltage at the terminals of the antenna. And that maximizes the amplitude. So if you put open circuit or as large as possible, you can get full credit for that. That's fine. And then for C, okay, here's where it starts to get a little more challenging. For a given RFIC with DC logic level VIC, average received power P sub R, and diode turn-on voltage V sub T. Derive an equation for predicting the minimum number of charge pump stages required to get to the design to work. Okay. So man, how do we go about doing this? Okay. Well, we have an expression for VA here. We know that VA is equal to, if it's conjugate matched, we've got 2 times the square root of 2 PR RA. And let's go ahead and leave in these variables. RIC squared plus XIC squared over RA plus RIC. That's my voltage. And what I need to do is VA minus VT is approximately equal to the amount of voltage that I need to clear the diode, that will clear the diode. I need VT to turn it on, and then I need VA minus VT to kind of make it over the hump. And that's going to tell me what the upper limit is for my DC voltage on that resistor, provided that it's a large enough resistor. We don't get some of those effects that we talked about earlier. And then I'm going to multiply that by N charge pump stages. And that needs to be greater than or equal to VIC. So rearranging and solving for everything, N must be greater than or equal to, rearranging this around, I got VIC divided by 2 times the square root of 2 PR RA RIC squared plus XIC squared and then what I should also do is round up, right? This is the ceiling function. Opposite of the floor function. So I put little divots here on my brackets, but I don't put anything at the bottom to denote that I'm going to take the largest possible integer of whatever that produces. And that'll give me a nice estimate of how many diode stages that I actually need. If I wanted to do this for a true matched circuit where RA is equal to RIC, then this would be, yeah, 2RA. 2's would cancel. Notice it does pay sometimes to have some leftover reactance. You want to conjugate it out in your total system, but at the terminals of the device, this will often increase the voltage and will allow you to increase the efficiency across the diode. But this would get you full credit on this particular problem. Any questions about that so far? Okay, move on to another problem. Let's do one on power optimized waveforms. It says, below is an approximate RF to DC conversion efficiency, N, eta, is a number between 0 and 1, for a charge pump system when the amplitude of a sinusoidal input VA is at least 3 times larger than the diode turn-on voltage. So we have a charge pump, and when you measure it on your RF test and measurement setup, the efficiency seems to be proportional to 1 minus 3 VT over VA for large VA. And it says, the question, if the power from a continuous wave sinusoid is converted with only 20% efficiency, then estimate what the conversion efficiency becomes when a power optimized waveform is used with the same average power as the CW waveform and an envelope peak to average power of 8. So peak to average power waveform of 8. Now keep in mind, VA power is generally proportional to V squared, right? So it's missing, it's not dimensionally correct, so we have to say proportionality, but power is proportional to voltage squared. It's not an amplitude. So if the peak to average power, that's defined as your peak power, and divide by your average power, that should be proportional to basically the square of your peak voltage divided by the square of your RMS average voltage. So if we have a CW voltage, let's call it V sub A, to be consistent with what the problem and what we've been doing on the board. If this is my RMS CW voltage, and my peak voltage should be the square root of PAPR times VA, right? PAPR is with respect to power. You got to take the square root if you're trying to find the ratio of voltages in that scenario. And so we have a waveform now that we know kind of what the peak the peak voltage is. It's the square root of 8 times higher than the RMS average. And now we also have an expression that that characterizes our device. We said at CW, there's only a 20% efficiency for this signal. Which means that VT, if you solve for the ratio of VA over VT, you get 3.75. Or in other words, VA is about equal to 3.75 VT. We're not given the turn-on voltage of the diode, but it turns out we're not going to need that for this week. That'll cancel out. And so then when we go to figure out what is the efficiency of a power-optimized waveform, say 1 minus 3 times VT divided by, well, now we've got something that's the square root of 8 times larger than VA. What is VA? 3.75 VT. VT's cancel, and when I finish my calculation, I get something that's almost 72% efficient. Dramatically increased. Okay, any questions so far? Does this example make sense? You see, a lot of the questions aren't really that hard. It's just a matter of getting comfortable with the physical quantities that you're dealing with, doing your unit analysis, understanding the influence of these different signals on electronics. Okay, let's see, I have another sample question here. Let's try another. There we go. So one thing we haven't done yet in this class is really talk about the full gamut of standards and protocols available to like a low-powered sensor designer or something. So for example, we haven't really talked about comparative analysis of 2.4 gigahertz Wi-Fi or 2.11b or Bluetooth or Zigbee or the cellular network services that can do data. We have talked about 915 megahertz UHF RFID and inductive RFID. Maybe I can down select some of the questions here. See how good of a designer you are. So we'll simplify this question to 2 answers, or 3 answers. UHF RFID, HF inductive RFID, or maybe active wireless sensor. Okay. So let's start. I'm going to give you a scenario. I'm going to read it out, and you tell me which of these technologies would be better suited for the job. And a lot of these are based off of real life scenarios. So we have a casino operator in Macau, probably, must sense the number and type of casino chips on a table in front of an individual player during his or her bet. The probing antenna is placed immediately under the wooden table beneath the small betting area and must reliably count up to 15 chips high. Which of these technologies, A, B, or C, is the best to use in that scenario? I think so too, yeah. In fact, there are casino chip counting technologies based on this. That you need to get through a table, which hopefully is not metal. You need to be able to read close in, so using something that's magnetic field based. Magnetic fields aren't disturbed by dielectric materials. It's obviously a short range technology, and it needs to be very reliable with a tight bubble of coverage, right? You don't want to count the chips on the table next to you. Then B is the way to go. Okay, let's see what's this next one. A FedEx truck must send back its identification and GPS coordinates in real time to headquarters for an online tracking application. You'd need the cellular network or something like that. So that would be a C. C. Let's see. Oh, here we have another gambling. A large hotel in Vegas must log expensive bed linens that are thrown down a laundry chute before they are taken off premises and washed by a third party. It is expected that a wireless radio at the end of the chute must read a small device sewn into the bed linen as it passes the chute opening. So you see that we have a very expensive linen. High-end hotels don't use the cheap stuff, right? They want you to have that nice hotel experience and feel luxurious and spend lots of money on their casinos, right? So maybe you went down to that Lotus Root looking building in Macau, and you're staying there and you're spending your millions of dollars after you become a rich and famous engineer, graduating Georgia Tech engine. And they take your sheets and they throw it down the chute, and sheets are expensive, especially if they've got high thread count. And hotels, in many instances, don't do their own laundry. They contract that out. Laundry trucks pull up every day. I once went to an industrial laundry facility out in western Georgia, just west of Atlanta. It was amazing, that operation. Gigantic warehouse. And trucks pull up in one giant bay of the warehouse, and they dump linens. And it could be anything from hotel linens. It could be the scrubs that doctors and nurses wear at hospitals. Nobody does their own laundry at these big, high, kind of big scale industrial facilities. And they get a big load of laundry in, and it would go in this conveyor belt that wound all around the room, and then it would dump off into this giant washer. And the washer was really it's like a 40-foot long barrel that corkscrewed the linens through slowly, rinsing it with blazing hot detergent, and then it would get off to the other end, and this giant masher would come down and it would smush all of the extra water out, and then it would dump through another corkscrew, and the thing would dry after 40 or 50 feet. And then they'd need to sort it and count it and route it back to the user. Well, you need a technology, first of all, that's going to survive the intense chemical bath and the super high heat and the high mechanical pressure of wringing out your industrial laundry, right? That's not your typical radio, right? If you have a battery in that scenario, Yeah, that's toast. Not to mention the fact that you have to replace the battery every so often. So chances are we're looking at one of the passive technologies, A or B. Which would you pick for that scenario? If you wanted to count linens coming out of a chute, A or B? This one's a little more subjective. I don't think there's a really hard metric for this. You could probably do it with either one. What's some reasons you might want to use A for that scenario? The inductive RFID, or the far field UHF RFID, 915 megahertz type stuff. Well, you get longer range, right? So you maybe have a bigger chute, you have an antenna over on the side of the chute and just count it as it goes down. One of the drawbacks though is what if these linens are wet already, right? Well, you know, if it's a dry linen, it's fine. Radio waves propagate that through that very easily. But if it's balled up in a mass and it's damp and wet, you could actually have trouble shielding your tags if the tag happens to be buried in that ball. And that would probably not be an issue with the HF system because it's magnetic. It would go through water. Anyway, I'd have probably accepted either of those answers. The actual problem has a list of like 7 different protocols for speccing out these different scenarios. So it wasn't quite as cut and dry as I'm making it up here. I just don't pick C. Okay, oh, here's a good one. Let's see. Oh, yes.
Could I ask why C cannot be used in this case?
So an active wireless sensor protocol would probably require a battery, right? That's what an active. So this would be like a Zigbee sensor or 802.11b sensor or Bluetooth low energy, something like that. That's one of the reasons why I use these passive technologies is that you're trying to glean information in an environment that's intrinsically harsh to electronics. Batteries tend to be a lot more sensitive than circuit boards or even like plastic insets with chips on them. Okay, here's another one. Let's see. We have a home keyless entry system senses whenever a person is within 3 meters of the front door. If the person has the proper wireless device transponder in their pocket, the door automatically unlocks. What do you think about that?
Do we need to select an option?
Yeah, which option? If you were the engineer designing that system, which technology would you pick?
UHF.
You would do a UHF RFID.
Or we can do it by active wireless.
Yeah.
Either of them.
Yeah, if I had to rank them as based on the specs that I've given, it has to work in your pocket. So keep in mind that's close to the human skin. You'll see that makes things very difficult in terms of antennas. You'll easily lose 10 dB or more operating close to the skin. So even though if this tag was floating in free space, you could probably use A, right? But that's a little dicey. So I think I would probably prefer, like you said C. Oh, thank you. Merry Christmas to me. I got a pencil.
But you see the battery will do harm to the will cause some problem for the steam or not?
Probably not, no. As long as you don't make it leak. So don't get Samsung to do it. Oh, that was mean. Apologies to any of my Samsung colleagues or friends watching this. There's probably like 4 distance learning students from Samsung taking this class right now. I had to make a battery joke. You do have to worry about changing batteries, right? But for this type of system, something low energy that basically turned on in the presence of a beacon and otherwise slept. You can get those things to last for a couple of years now, at least 3-4 years, on a single coin cell type battery. And obviously, the HF inductive RFID, that's always nice for passive systems. You don't have to worry about it on the human body, but you won't get a range of 3 meters. Unless you've got a red hot inductive coil around your door or something like that. Okay. These are kind of fun, huh? Designing applications on the fly. Some of these are actual RFID or sensor applications I've seen from industry walking around, and other ones are to various degrees of success, senior design projects that Georgia Tech students have attempted. Let's see, here's another one. Oh, here's a good one. A large theme park is installing wireless video cameras across its theme park. These cameras will be mounted on lamp posts to provide security video over every part of the theme park. What should wirelessly communicate with the wireless video cameras? Definitely C, right? Because you just can't, we don't have enough energy to do, forget the range requirements. Even when we do get the ranges that A and B work with, we still don't have enough power to drive things like video. Not yet, anyway. I've met people that say, you know, if we drive enough, we could actually make an extremely low-powered camera or even a video system. But those days are in the future, not now. Okay, here's another one. Hundreds of small chemical sensing devices are sprinkled around an airport to detect the presence of toxic gases, protecting us against terrorists. These devices form an ad hoc network. Do you know what that means? They communicate with one another. So it probably eliminates A and B on this already, right? And communicates to provide anti-terrorism and monitoring. So this would probably be good, like 802.11b type network that can operate in peer-to-peer. Yeah, Zigbee down there. Okay, let's see. What's another one? H. Let's see. A motion capture gaming console must relay identification and accelerometer data from player remotes for a virtual basketball game. Up to 10 players must be accommodated simultaneously. So you have this really cool video game where 10 people can put motion capture sensors on and run around and dribble the ball. And I don't know why you wouldn't just play regular basketball once you got that involved. But maybe this is
shorter than
yeah. Do it in your living room. Yeah.
Something like a Wii.
Yeah, yeah. That's probably the inspiration for this problem. A Wii. So this one says Bluetooth, short range, probably powered because you've got to drive peripherals and things like that over more than just a very short distance.
But you can use Zigbee as well.
Probably, yeah. Yeah. I think some of these I would accept multiple protocols as long as there was some justification. Okay, here's the one. We got two more. An engineering design firm proposes a small, low-cost, no-maintenance device to put in a vehicle windshield so that residential cars may automatically open and enter a gated area. Yeah, I would say A. That's essentially an AVI system, automatic vehicle identification system. It's got to be no maintenance, no battery. That means no battery.
Passive.
Passive. And generally, if you put it on the windshield, you need far field interrogation to get that to work. A cruise line, here's the last one. A cruise line wishes to install a location sensing system on their ships which detects the presence of people wearing moderate cost wristbands. So you just have something on your wrist. A sudden absence of the wearer on board of the ships is used to predict a man overboard condition. Nothing kills a good cruise like falling overboard and being forgotten in the sea, right? So if they give you this wristband, then they know if you're still on the ship or not. Maybe they can also, maybe it doesn't have to be life or death. Maybe they can also leave a port when all of the heads are accounted for on the cruise ship. So what would this one be? Well, it wouldn't be HF inductive, right? Because the range isn't close enough. Unless somehow you were able to magnetize the whole ship. That'd be a cool thing to do. Put a loop around the ship and try to power it. But it probably would be prohibitive. And of course, ships are metal anyway, so depending on where you went in the ship,
Sure.
you'd be shielded from radio waves, which means the path loss is probably pretty high too. Unless you could plaster every room with RFID readers, you wouldn't want to use A or B, you'd probably want to use C. Yes?
That wristband is a passive device or active device?
It could be either one.
That's what we need to decide, right?
Yeah, that's the question I posed to you. Should that be passive or active? Based on what we know about propagation and energy levels, it probably can't be passive because you would need too many exciter nodes around the environment, and in that case maybe a small coin cell battery would be sufficient to drive something that would, the duty cycle wouldn't be very high, right? You just ping, 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 turn on every couple seconds and send out a beacon. So you could do something that operated on a coin cell and would probably be good for months on end. But I don't see a way to do that passively yet. Okay. Any other questions? Well, that was fun. I don't have any other questions for you, so if you want, you can get going and studying.